welcome everyone to this first class of NPTEL course Principles of Polymer Synthesis. In this particular course, I am going to cover, as the title suggests, the basic principles of the synthesis of polymers. So, lot of chemistry aspects will be covered, and of course, considering the constraints of the course, for example, 20 hours, certain special applications also will be covered, and so most of the important aspects will be discussed as far as the principles of the synthesis are concerned. The way I have structured this course is like this. In this first class, I am going to give you an idea about the historical development of polymer science, how it came about. Everything just did not appear out of blue. So, it took decades of honest efforts from scores of scientists in order to establish what we now know as polymer chemistry and what we now take for granted as the structures of polymers. So, basically the main focus of this particular course will be on the structure property relationship. What are the structures and what are the kinds of properties that could be generated from these kind of structures, the kind of predictions that we could make out of them. And not only that, as the title, again as the title of the course suggests, it is how do we synthesize these polymers, the general principles of some of the most important polymerization processes will be discussed. So, we will now start with the first class. The topic of this class is historical development of polymer science. So, what are polymers? These are long chain molecules and identical or nearly identical units held together by covalent bonds. So, basically we have many units, hundreds of units or maybe thousands of units which are termed as monomers, as you know now. These are termed as monomers, and these are all connected through covalent bonds. For traditional polymer materials, there are materials which are supramolecular polymers, where all these units are connected through supramolecular associations, reversible bonds or pi-pi stacking interactions. You could have hydrogen bonding interactions, so on and so forth, which can be broken and reformed reversibly. We are not in general concerned with those kinds of polymers. More traditional polymers, covalently bound monomer units strung together to form polymers, those are the polymers we are going to discuss. So, this is the general definition that I have actually framed here: identical or nearly identical units that are held together by covalent bonds. Now, here I have actually classified the polymers based on their sources. Like we could have natural polymers which could be based on say polysaccharides, lot of sugar units covalently bound. They could be based on natural polymers, they could be proteins based on amino acids, or they could be nucleic acids, natural rubber, so on and so forth. Or based on the source, we could prepare the polymers in a completely synthetic, in the laboratory we can make polymers which are not natural, synthetic polymers. It could be polyethylene, polystyrene, nylons, etc. Some of these you probably already know as far as the names of these polymers are concerned. Or it could be semi synthetic polymers, like natural polymers we modify them with different groups, functional groups, say for example cellulose, nitrate, acetate, etc. Now, by no means this is the only way to classify polymers. There are different ways to classify polymers, to which we will come slowly. But the reason I am talking about polymers to start with, I mean I have not yet talking about historical development. I have started with polymers themselves, some examples of them. This is just to illustrate what are the recent things that we talk about in polymers, means what we know about polymers, and then we will try to impress upon you the fact that some of these things which we know now as very simple things, like the covalent bonds and all between small monomeric units, which we have come to accept as the facts, were not very easy to establish even 100 years back. We will come to that slowly. Now, this slide is about the importance of polymer industry, as the title suggests for this particular slide. Now, more than half of the total output of organic chemical industry, if you look at organic chemistry, the industry, it is contributed by the polymer industry, more than half of the total output. Only a few polymers actually account for this. So, you can understand what is the importance of polymers. Here are some data: 41 million metric tons of thermoplastic resins produced in the USA in the year of 2000 only. And there is polypropylene, high density polyethylene, linear low density polyethylene. Out of, say, for example, more than half of the total output of organic chemical industry, what we say as the polymer industry, in this around 40% already is contributed by some of these polymers. And as you can see, these polymerizations are affected with transition metal catalysts. Then combined output of 40% is provided by LDPE, low density polyethylene, polyvinyl chloride, polystyrene, polyvinyl alcohol, PMMA, which is polymethyl methacrylate, so on and so forth. And these polymers are produced by free radical pathway, or you can say some of these polymers basically are produced by chain polymerizations. We will talk about that in detail as we go on. And rest of that, which is a combined output of 18%, polyurethanes, polyamides, polycarbonates, PET, PBT, so on and so forth, those are from step polymerization. Here, as you can see, that this kind of distribution that I have made. So, different synthetic procedures are used for preparing some of these different polymers, which are most commonly used, and other less widely used polymers are there: acrylics, cellulosics, silicones, polysulfones, etc. And then there are also specialty polymers like polyether ether ketone, which is termed as PEEK, polyether ether ketone, or polybenzimidazoles, those kind of things. Here what I would like to tell you also is that this is okay, but the kind of things that we are going to discuss in the course are going to be something like this. So, these are the classifications we could make of different kinds of polymers. Say we have what you call as commodity polymers, we have engineering polymers, and we have high performance polymers. So, in commodity polymers, under the class of commodity polymers, we could talk about low density polyethylene, high density polyethylene, then polypropylene, polyvinyl chloride, polystyrene, etc. General household applications. These polymers are used for general household applications, and these are not mechanically very robust polymers, and the temperatures that they can withstand are also limited, say 100 to 120 degrees Celsius approximately. Now, and some of the applications, for example, they are used for packaging, they can be used for clothing materials, or they can be used for, say, plates, making plates or cups, medical trays, so on and so forth. Now, engineering polymers, they have more robust mechanical properties, and they basically can withstand higher temperatures, say in the range of 200 to 250 degrees Celsius. Again, they are like approximate temperatures, and they basically have better load bearing capacity if you compare with commodity polymers. The production cost is generally higher, and some of the polymers that will come in this category are polycarbonates or epoxies, acrylonitrile butadiene styrene copolymer, which is ABS, or polyethylene terephthalate, which is PET, or polybutylene, polyoxomethylene, so on and so forth. And lastly, there are high performance polymers, which can also be called specialty polymers. Specialty polymers, those could be like PEEK, polyether ether ketone, or polyamides. or polysulfones. They can withstand even higher temperature. They have very good mechanical properties generally, and they are very costly to make. So, only in case of special applications. So, these are the three separate classes of polymers that we are going to discuss later on as far as the synthesis of these polymers are concerned, as far as the structure property relationship of these polymers are concerned. So, after this kind of background, after giving you this kind of background, now it is the time to talk about some historical development, because as you can see that polymer industry has come a long way. We can actually prepare whatever structures we want, we can actually generate many properties, engineer many different properties. It may be requiring more cost depending on the class of applications that we envisage, but we can do that, and we can characterize the structures also very well. Those kind of things were not available even 100 years back. So, I am going to give you a little bit of peek into that kind of history. That is how I have designed this particular class. So, I will go back to that. So, in this slide I have listed a number of experiments that could be considered as the earliest significant polymer experiments. For example, in 1805 it was observed that natural rubber, when it is stretched, it generates some heat, and when it is under stretched condition, that means it is loaded with a load, then it will contract when you are heating this material. At that point of time, it was believed that an absorption of calorific fluid occurs when you are heating a loaded sample. An absorption of calorific fluid occurs, and that helps the material to contract, much in the same manner as, for example, when you put water into the ropes, they will contract. And the next event that I wanted to mention was in 1826, when Faraday analyzed an aqueous suspension of rubber latex. So, he was correctly able to show that this phase contains proteins, and he was able to comment on the elemental composition of rubber also. And not only that, amazingly, he did an experiment where he heated this rubber with sulfur, and he observed the generation of hydrogen sulfide gas. But this is something that he explained away as, you know, it is a way to reduce the amount of hydrogen in a material when you heat it with sulfur. So, this was one of the greatest opportunities missed. You know now that this is nothing but vulcanization of rubber, where you can put sulfur into a generally tacky natural rubber material, and then it has cross linking, and that renders it elastomeric. That means, it can be stretched to a higher length, you remove your force and it comes back to its original configuration. And afterwards in 1839, it was shown that when you distill styrene, there is a residue left which gains thickness with time, and it was believed that it is nothing but styrene oxide. And later on it was also confirmed that in absence of oxygen also this particular observation was there. That means, it was not styrene oxide, but it was some compound of styrene. They failed to realize that it was actually a polymer of styrene. Okay. So, with this kind of introduction, now I would like to tell you something else, how this particular field developed in a way that lot of other experiments were done. These were some of the main experiments, lot of other experiments were done, lot of other polymers were made in the 19th century, which were, you know, commercially viable, but they did not realize that they were polymeric materials. So, I am going to give you an idea of what occurred around that point of time. So, around 1839, Charles Goodyear, he actually described the vulcanization of rubber. Vulcanization of rubber. So, that was the birth of rubber industry. Now, something I want to mention here, that up to late 19th century, whatever polymers were made, they were actually modification of natural polymers. So, chemically modified natural polymers, all of them were like that. An example could be the nitration of cellulose. Cellulose is a natural polymer. Now, this nitration was described way back in 1833. and afterwards in 1847 this was controlled in a controlled fashion, this nitration was done, and then smokeless gunpowder was developed, which was used as explosive. And later on it was found that if you add camphor to this, to nitrocellulose, if you add camphor, this camphor has a plasticizing effect on nitrocellulose, and that renders the nitrocellulose melt easily processable. And these kind of materials were later used for the films for the cinema, and these were very highly flammable. So, it was not a coincidence that there were many incidences of fire that were reported from the cinema halls. And these class of materials, this nitrocellulose plus camphor, this class of materials are known as celluloid. You may have heard about this particular term. So, celluloid films were in vogue at that point of time. Now, first major discovery as far as the synthetic polymers were concerned was in 1907. I have a slide for this after, that was by Beckland, where he discovered a way to control the condensation of phenol and formaldehyde, and he generated the first fully synthetic polymer, which was known as bakelite. Now, this bakelite that he had generated, this he commercialized this under the trade name bakelite, and this material was an excellent electrical insulator. So, many different uses were envisaged for this particular material. So, say this is the slide which describes actually the material. So, it is a network formed from phenol and formaldehyde, and from starting from telephone to radio, many of these materials were made from bakelite. So, this was the first fully synthetic polymer that was made. But what about the name polymer? If you look at this particular name, this name was coined long time back in 1833 by Berzelius. So, at that point of time what he talked about is polymers are compounds of the same chemical composition, they exhibit different properties. So, those are not in a traditional sense of way the polymers that we know now. So, they included isomers, they included homologues, they included polymorphs. So, those were not the real polymers that we talk about now. The real revolution happened when Hermann Staudinger entered that field. So, in the early 20th century, all these properties of polymers, like they are highly viscous, like they have low diffusion coefficients, or some of them are very difficult to crystallize, they were all explained away by saying that this could be you can explain this by the formation of colloidal aggregates. Small molecules could associate and they can form aggregates, and these aggregates can explain everything. And this is something that all of this changed when Hermann Staudinger, a German chemist, he came into the picture in 1920s. He theorized the existence of very long chains that are held together by covalent bonds with molecular weight reaching hundreds of thousands. So, this is something, this particular concept, this is something that met with lot of resistance at that particular point. Now, I will give you an example of how the structure of natural rubber was basically explained without considering that it was a polymer. So, if you consider, say for example, natural rubber, in 1905, it was described as a material that consists of this molecule cyclooctadiene, dimethyl cyclooctadiene. So, several of these molecules can come together, several of these molecules in this fashion, and they can have this kind of interaction through partial valency, and this material. So, you know this kind of association of small molecules, not necessarily a polymer, and this could explain the properties of rubber. That was what was claimed. But what Staudinger showed basically is like this. You have a double bond here. So, if you hydrogenate this double bond, and if this particular theory is true, then you can actually get small molecules, but that was not the case. Now, we know of course. So, this is rubber, we have polymers of cis isoprene. This is what we know. So, what he did is that a hydrogenation of the double bond, and when you do a hydrogenation, we did not get any volatile compound or any cyclic product, and this material has similar property as natural rubber. So, what he concluded is that the material that is produced after hydrogenation of this natural rubber has very similar properties, and they are also macromolecular in nature. So, I am using this term macromolecule here. This is the term that was introduced in 1920s by Staudinger himself to explain the properties of these materials. Now, some of these things actually encountered lot of resistance, and rightly so, because at that point the understanding of structures were very much limited. Okay, I will go to the next slide and I will explain to you a few comments. So, Heinrich Wieland, who got Nobel Prize in 1927, he told Staudinger a friendly advice that abandon your idea of large molecules. Organic molecules with molecular weights exceeding 5000 do not exist. What Wieland believed is that at that the rubber that you have, if you it's basically an impure material. If you try to purify this material and you can purify it properly, then you will get crystallized materials with small molecules. So, he advised Staudinger that large molecules do not exist. In a public debate at a conference in Dusseldorf in Germany, September 1926, one of the chemists actually mentioned that zoologists will be shocked if they found that in Africa somewhere an elephant was found which is 1500 feet long and 300 feet high. We are also shocked the same way. The idea of polymers like this long chain with all these molecular units connected together by covalent bond is pure nonsense. But later on, of course, you know, after all this resistance, as you know, Staudinger showed through hydrogenation that of course, the cyclooctadiene theory is not right for rubber. So, after hydrogenation what you get is the same compound, and one of the things the crystallographers believed also at that time is that the polymer molecules are so big they cannot fit into a small unit cell, but it was shown through crystallography. The Staudinger himself showed this for polyoxomethylenes, that part of the molecule can actually be accommodated in a unit cell and still it can be a polymer. So, it is not a problem, full molecule did not be in a unit cell, and so crystallography aided actually Staudinger's hypothesis a lot. And in 1930s, in between 1930 to 1940, Carothers made nylon the first synthetic fiber. Hundreds of molecular units were joined together through covalent bonds. It was unambiguously proved, and also there were industrial developments of polystyrene, PVC, polyvinyl chloride, polyolefins, polymethyl methacrylate, and that also culminated into Ziegler-Natta polymerization, which was discovered in 1953, you know, for high density unbranched polyethylene and isotactic polypropylene with specific stereoregularity. Those things were also discovered, and the Nobel Prize was awarded in 1963. So, ultimately all of these things tell us that Staudinger himself and some of the other chemists at that point of time, they had to undergo lot of struggles, and I would like to conclude this class by quoting from the Nobel Committee's announcement for Staudinger. In 1953 actually he got Nobel Prize for his enormous contribution to the development of polymer chemistry. So, Professor A. Fraser, a member of the Nobel Committee, he actually summarized his achievements by these words: "It is no secret that for a long time many colleagues rejected your views, and this was understandable perhaps. In the world of high polymers almost everything was new and untried. Long standing established concepts had to be revised or new ones created." So, the development of macromolecular science does not present a picture of peaceful idyll. So, I hope that I have given you a glimpse of how the polymer chemistry was developed, how for long time people had been actually working on polymers without actually understanding the structure of it. They were thinking it was composed of small units, but they could be held by non-covalent forces like colloidal aggregates. And later on Staudinger came, and in front of lot of criticism and lot of resistance, he established his theory, and it was actually ultimately shown that polymers with long chains can be created. And the final example that I would like to give is of Emil Fischer. In the early 1900s, he was a pioneer of protein chemistry. So, he had made a long polypeptide, I guess 17 to 18 amino acids joined together to a tedious synthesis. So, that itself should have shown to him and others that polymers are indeed possible, but even he was skeptical of these kind of ideas, and he thought that molecules exceeding molecular weight of 4000 could not exist. Nowadays we know hundreds and thousands of Dalton of molecular weight of polymers are available. So, with this I would like to conclude this particular lecture, and what I would do in the next lecture is to go into the classification of polymers and slowly try to talk about how you can determine the molecular weight of these polymers. Thank you.